Hey, what's up guys, my name is the Cherno. Welcome back to my game engine series. So last time we talked about blending, make sure that you check out that video if you haven't already. And today we're going to be taking a look at our code and figuring out a better way to do something that we did before. Seems like this is kind of the way the programming goes in general. You write some code and then a little ways down the road you figure out that, well, actually this kind of sucks, there's a better way to do this. Now of course, this isn't me specifically like accidentally writing bad code and then being like, oh my gosh, there's just such a better way to do this that I've missed. It's more or less me just building Hazel incrementally, or rather, I guess, iteratively. And that's very common when you're building software, to iterate over what you've already got and then change it as time goes on. The reason is that our goal here kind of is to try and build up like an MVP, a minimum viable product, we'll say, as quickly as possible, and then kind of retrace our steps and make things a little bit cleaner. So I mentioned this a really long time ago, I think when we created our first triangle, where basically what I want to do is I don't want to spend a year writing code that is then finally going to produce a triangle for us, but the code's going to be rock solid. That's not fun for anyone. No one does that really. I've never heard of anyone doing that before because it's weird. What you want to do is write that triangle basically as quickly as possible, right? Not being completely crazy, right? I mean, if we wanted to, we could just write everything in one file and we wouldn't have an engine, but we'd have a triangle, right? I'm not saying do that. I'm just saying get that triangle as quickly as possible in a reasonable way, right? And then we can retrace our steps, go over that code and improve it and make it more robust and just better. And that's kind of what we're doing here. In the shader episode, right, we wanted to basically load a shader and use the shader all within like 20 minutes and just have it running, and that's it, right? What we're going to do today is retrace our steps as to how we actually, compile shaders and basically change it so that instead of just taking in two strings, a vertex source string and then a fragment source string, we're going to load it all from one file. And this is going to be super simple. In fact, I made a video in the Opengl series. It's called How I Deal with Shaders in Opengl. Check that out because it's going to shed some light into what we're going to be doing here today. It's going to be slightly different than what I did in that video, but like for all intents and purposes, it is going to be the same. So recently we talked about assets and we kind of introduced textures as our first asset, and that was fantastic. But now what we can do is actually go over to our engine and take a look at other things that should be assets, namely shaders, right? Shaders should not be kind of just defined as strings. Maybe it should be possible for your API to support that, because who knows, maybe someone wants to build an application in Hazel and they want to have a little text editor in IMGUI, or maybe a custom control that's like a text editor, and then you can like write some shader code in and then you can just like see the effects of that live, almost like Shader Toy or something like that. As a Hazel application. That should be possible, right? I want to make Hazel as open as possible. I want to make the API as powerful as possible so that you can do things like that. So in other words, we probably still want to keep I was going to say opportunity, but we want to keep the capability of compiling shader code from strings. We still want to keep that, but we want to introduce another way of creating shaders, and that's going to be from a single file, a shader file. Now, look, if we talk about other APIs, other rendering APIs, not just Opengl, typically speaking, like you wouldn't compile shader source code very often. Like you would have maybe pre-compiled byte data essentially that is kind of your binary shader, and then you just, run that, for example. You could compile it on a target platform because commonly, if we look at large scale games, right, what they'll do is they'll actually ship with There'll be like 1 billion permutations, and then based on your target hardware, it will take the appropriate sections, and based on what graphics settings you've chosen as well, it'll take appropriate like shader blocks and then combine them all into a shader locally on your computer, right? And then it'll cache that as like a cached shader, and then that's the binary data it will load at runtime. That's typically what happens. Obviously, we're nowhere near at that stage yet, but for us, we're going to kind of ignore that. As far as I am concerned, I don't think Opengl supports binary shaders. I'm not 100% sure. I haven't gone that far into Opengl itself because, as I mentioned, like Opengl is quite a simple API. I don't usually like dealing with it too often, but for the purposes of this, it's just fantastic. Obviously, I'm not hating on Opengl at all. I'm just saying that professionally, I haven't like gone into there too far because, no one really ships games for Windows on Opengl. Like that's just not something that's done. Anyway, my point though is that you know, with Spur V, maybe you can do something like that. I'm not 100% sure how all of that works. So if you know, leave a comment below, because I will investigate this, and I'm sure that a quick Google search could clear this up for me, but that's besides the point. So what we're going to do is we're going to take a look at creating shaders as a resource today, which is going to be really, really cool. It allows a few things, right? First of all, these are strings right now. They're static strings in our memory, right? That's fine, but the cool thing about having files is that it's almost like we've introduced a scripting language. What we should be able to do, theoretically, and I mean, well, we will be able to do this, 100%, but theoretically what we should be able to do is actually take that file, make some changes to the shader, go back to Hazel, and we should see those changes live, right? There's no reason for that not to work. All we have to do is recompile that shader, right? Done. Reload the file, recompile the shader, and then activate that shader instead, right? I mean, if there are errors in the shader, maybe don't recompile it, maybe just display a message being like, couldn't compile shader, but still keep that original shader until we actually get one that compiles successfully. But my point is, reloadable shaders, something that should be really easy with this system. So there are benefits to it. It's not just the fact that I don't want strings here and I want separate files. It's also, which would be necessary, who wants to have strings as shaders in their code anyway? But my point is, it comes with other benefits that you may not see. I want to give a huge thank you to all the patrons that made this series possible. Patreon.com/the Cherno is the best way to support the series and everything that I do here on YouTube. People who do help support the series get access to something called the Hazel Development Branch, which is a way more advanced version of Hazel with like 3D rendering and all of that fun stuff. I have already done this kind of reloadable shader system in that code base, so this will kind of be inspired by that, and in fact I'll be taking code directly from Hazel Dev in order to make this stuff happen. Anyway, let's get into the code and see how we can change our shader workflow. So these strings here are exactly what I'm talking about. I don't want to have these two strings here. It's kind of annoying, right? I still want to be able to do this if I really, really have to, but I don't want to have these two strings here. I want to have them in a file. Let's talk about what that file might look like. I think the best way to write this kind of stuff is to first determine what is the end result, right? It's the same thing as when you're running an API. You know, instead of going in and trying to create a shader class, just start typing code like shader, you know, create, and then, you know, okay, I guess I'll pass in like my files. So for example, in this case, we could have assets, shaders, and then, well, let's just see, what are we actually using out of the shaders? We're using the texture shader. So we'll say something like texture.glsl, right? And then that's it. That's kind of how we want our API to look. So in that same spirit, right, what we want to do is do the same thing with the shader. So I'm going to create a shader first before we even take a look at the code that we need to both load it and read the file from our disk, and then also kind of split it up into two shaders, because as I mentioned, of course, Opengl wants two different strings, but we're going to supply everything in a single file because it's going to be super clean that way. Okay, so if I show all files here, we take a look at Sandbox. We've got assets, textures. I'm going to make another folder here called shaders because that's where I want all of our shaders to live. And then inside there, I'm going to make a new item. I can just use Visual Studio to do this, or of course you could just do this in your file explorer if you wanted to. And we're going to call this texture.glsl. Now I've called it GLSL specifically. I don't want to call it like .shader or anything like that. You can call it anything you want. Obviously it's just going to be read in as a string. But the reason I've called it GLSL is because this specifically is GLSL code. That's important because in the future, it's very likely that we'll stick with a single shading language, most likely HLSL, which is like the DirectX shading language. And then from there, we can cross-compile it into GLSL if we need to, using something like SpurV. But anyway, that's way in the future. We're not going to bother with that now. But basically what I'm saying is we still want to keep this as GLSL, because it's going to be useful that way. Now, in the future, in the more immediate future, before we talk about cross-compiling and other APIs, it's very likely that we'll actually modify GLSL and kind of turn it into our own shading language, because it's not that difficult to do. And basically, it will just enable us to have a few more like keywords in the shading language that will help Hazel kind of know the intended usage of certain areas. So that's something that will probably happen, I would say, sooner than like cross-compiling and all of that fun stuff, but we'll see, because I don't want to promise anything, because I haven't really gotten around to that yet anyway. So let's look at what we're doing. So we're dealing with our texture shader. We'll start with that one, right? What I'll do is I'll copy, this is the fragment shader, right? I'll copy that, paste it here, and then I will do the same thing with this vertex shader, and I'll paste it in. So So we've got two shaders here. Obviously we need a way to distinguish between what type of shaders they actually are, right? So this is a vertex shader, and then this is a fragment shader. The way that I like to do this is just to type in the word type with like a hash here, just the same way that we have hash version as like a preprocessor kind of directive, we have the same thing with type. And then I'll just type in the type, right? So this will be vertex. And then for this one, I'm gonna call it fragment, because it's a fragment shader. Now, you might call it a pixel shader, that's fine. I'll probably end up supporting both keywords. But basically what this will do is have a little indicator for us being like, okay, the following is going to be a new shader type. Keep going until you either see another type or until the end of the file, right? And then the next keyword here is going to be the type of shader that it is. So vertex, fragment, pixel, geometry, whatever, compute, whatever it might be in the future, will kind of support that as well. And then that's it. Now, how lovely is it, can I just point out, to have both of your shaders in a single file, right? I mean, I hate having separate files for shaders. DirectX has it usually as a single file as well, which is super useful. But OpenGL likes to split it up. Very commonly, people will load their two different shaders as two different files. That's super annoying, and I don't see the point of that at all. You could argue that yes, you could reuse the vertex shader for many pixel shaders, but in my experience, like, I don't know, I don't think that's that useful, because commonly when I've been modifying the pixel shader to do something else, I've had to modify the vertex shader as well. Like maybe I've got different uniforms, maybe I've got a different vertex layout. That all requires modifying that vertex shader anyway. So commonly, I wouldn't say that there have been too many cases in my life personally where I've been like, I've reused the same vertex shader for like 500 fragment shaders, for example. That's not gonna happen typically, right? Obviously, if you have a system in which you assemble shaders from blocks live, then you'll very commonly reuse the same vertex block, but that's something completely different. And in that case, you would still load the one file anyway, so it doesn't matter. Okay, anyway, texture, there. We've got the texture shader, fantastic. I'm just gonna delete it from here because I'm that bold, and of course we will get this to work today. So if we go over here into, basically I'm just gonna hop over into shader create. I'm going to add another shader create. So I'm not taking away the existing functionality because I do want to keep that in case we want it. And then Windows 10, just go away, please. I really am really close to switching to Mac or Linux. So there's our shader create function. We've got our path. I'll just call this file path to make it super explicit. We'll come over here. I'll just implement this function here quickly. And follow along with this. It really should be the first function, I think, because we did put it in that order in the header file. Then I'll copy this, and I think we'll just tab this across. I think this just becomes file path. I think this just becomes file path, and that should be it. Okay, Opengl Shader from a file path, done. So if we hop on over to Opengl Shader, again, we will duplicate this constructor and just make it a file path constructor. And then if we go over to the CPP file, we can take a look at what we need to do. So we do everything in the constructor right now, which is fine, but not really what we want. So what I'll do is I will probably make a function, a private function here called compile. And this is what will do basically everything that the constructor did. So compile, and then we probably want to take in the source code. So let's take a look at how we're going to split this up first. And in fact, what I'll do is I'll kind of have, probably what will happen is both of these constructors will actually, IntelliSense takes forever. Both of these constructors will actually just call into that compile method, and then this already has it in the right format, which is fantastic. But then the other constructor, which we will create right now, the other constructor will of course have to read the file first. So we'll have our file path here. Okay, so as for reading the file, let's get that out of the way quickly. So basically what we want to do is take in an input file stream. Now, look, I mean, in the future, a file system in a game engine is a very complex topic. Like, you'd usually have like a virtual file system. You'd usually have to abstract this because obviously it's going to be different on Android or iOS versus Windows, and so you might need to like mount certain directories, treat it like as a virtual file system. You know, you might have all of your assets stored in one binary blob, and then you might have to go in there, and it'll probably be compressed as well. And so there's a bunch of things that you need to consider. But obviously we're going to be keeping it super simple here, and really we're just going to use an IF stream. This code in the final ever version of Hazel, right? Hypothetically, I don't think this will make it, right? It will be completely different in that. I mean, realistically, we might even have a per platform file system. So we'd be using something like Windows, like create file, you know, or whatever, to actually do everything that we need to do, instead of using the ZPP library. So don't worry if you think this is final code, it's definitely not, but it's gonna get the job done for now and probably for the foreseeable future, for a while, because it's definitely gonna be good enough for us. So we'll take in a file path, and then we will just tell it that it's an input file, and then that we want it to be read as binary. Now, you might be like, why on earth are you reading a text file as binary? It's because we don't want to do any processing to it, right? This is going to be completely just in the format that we want it to be in. We want to read all of the binary data so that we actually get all of the data from the file. We don't want C++ to take it and try and interpret it as a string. That's completely unnecessary and something that I definitely don't want to have. So we'll just include fstream here, and we should be good. So if that input file stream was successfully opened, if it's not, we could assert it, because really you shouldn't be trying to load files that don't exist. So what I'll probably do is just write a little warning here. The reason I'm writing it, well, I guess we will make it an error. The reason I'm not asserting is because maybe this might be permissible. Like, you might try and load a whole bunch of shaders. If they don't succeed, that could be fine. Like, we should still be able to handle it, I guess. But anyway, could not open file, and then I guess we will supply the file path as a argument here. Okay, that should be pretty good. Oh, whoops, totally did not close that quote correctly. All right, so now we've got our core error, which is great. So the first thing I want to do is actually see what the file size is, and then our strategy is going to be to create a string that is that big and then load everything into the string. So we'll do in seek g, and we'll go to the very end of the file. So offset of 0, and then to iOS end, right? This will go to the very end of the file. So now our kind of file pointer is at the end of the file. Then ideally I want to like basically create my string. So we'll actually create the string here. We'll call this, I'll call it result, and we'll move this into another function because it's getting a bit too messy here anyway. So we'll resize the result here, and this will just be tell g, which will basically tell us where that actual pointer is. So thus, since the pointer to the file is at the very end, it is the size of the file. Now we need to basically bring us back to the start. So begin, and then we can read the file by just calling in.read. We're going to read it into the very first, we'll just give it a pointer to the beginning of that string. And then of course the size of the string, which is the size of the file, will be our size. So we're reading in that many bytes, it's going right into the string. We've obviously resized the string into the size that we want, and that is pretty much it. And then obviously at the end, we will close that stream. Okay, that's it. Now all we need to do is process this result. So what I'll do is I will make another function here called read file, and of course we'll take in a file path to read. I'll copy this and I'll put it probably just below the constructor here, or maybe below the destructor, and Opengl Shader read file, and then this will just basically be the contents of this, right? Okay, cool. So there we go. At the end, we'll return result. So we'll return an empty string if this was not able to be read, which is fine. And then we can call read file. And then now from file path, we have our string for processing. So we'll have this our shader source. Okay, there we go. So now we need to actually split it up into the appropriate number of shaders. So we have our shader, which has two different types here. We now need a function that will basically read through that string, and then based on these two types, split it up into two strings, where one string is this section over here, and then the other string is this section over here. So let's go ahead and implement that. What I'll do is I'll create another function here before compile. I'll call this pre-process, and this will of course take in our shader source code, so string source. Now, what we want to do is split it up into multiple shaders, as I've mentioned. So we need a way to organize this. We could just use something like a pair or a tuple, or we could create a struct that has all of our different shader source codes. However, we don't even know how many we want, right? Because this could contain two shaders, a vertex shader and a fragment shader. It could contain more, right? For example, we could have a geometry shader in there as well. Therefore, that would be 3 shaders, right? So because of that, what I'll do is I'll actually use a map, specifically an unordered map. And what this will do, unordered map, is basically map us from a GL-enum, which is going to be the shader type, and we're storing it as a GL-enum so that we can immediately just give it to OpenGL as so basically the key of this map is going to be the type of shader that we compile, and then obviously the string, which is going to be the source code. So that's going to be our pre-process. And when we go into compile, that's what we will take in, right? We'll take this in by const reference, and this will just be our shader sources, okay? So back into C++ land, well, I mean, we're always in C++, but I mean into the CPP file, we will implement this function. And now let's talk about how this is going to work. Okay, so what I've done here is I've cheated a little bit. I've taken this code from the Hazel development branch because it's already written and there's no point in me writing this for you. I will explain all of it in a minute. There is one function that still needs to be implemented, and that is the shader type from string. That's really simple. All that does is just convert a string to a shader type. Super simple function. We'll implement that right now. In fact, I'll just do this at the top of this file. Doesn't even need to be in the header file. We'll have a static GL-enum, and then let's see, what was the name of that function? Shader type from string. This will of course take in a const string, which is going to be our type. And then if the type is going to equal vertex, so this is just the final kind of type, right? So what we see at the end of this, so vertex, fragment, all of that kind of stuff. So if it's vertex, we'll just return GL vertex shader. And then if it's going to be fragments, I'll actually tab this down because it's going to be a long line. If it's going to be fragment, or we'll support pixel as I mentioned before, we'll return a GL fragment shader. And of course, if we had other shader types, then we would return that as well. If we haven't returned anything, we'll just do a core assert here, and we'll basically just say that it's an unknown shader type. And then I guess we'll actually have the type here as well. We can't format this, can we? Yeah, that's going to be a little bit annoying. Okay, in that case, I will just write unknown shader type. We need to probably fix that so that we can actually format things like this. But anyway, there we go, unknown shader type, and then we'll return 0 for our value. Okay, sounds good. We're back here. Let's talk about how this code works. It's really quite simple. So the first thing that we do is actually figure out basically the token that we're going to split on. So type is the keyword that we're looking for. Hash type, that basically tells us that after that token, the next token is going to be the type of shader, right? So what we do is we try and look for the type token through all of our shader source code, right? At this point, this is all of this code. And then if we find it, right, or in fact, while we keep finding it, because obviously we'll look for it as many times as it exists, we'll start with the top of the file and we'll kind of go down. And for all of the types, we want to find them all. So while we still have found that type token, so for the first time that we run through this code, it will be literally on the first line, right? What we'll do is we'll find the new line, the first instance of a new line or a carriage return. This will find either, right, which is what we want. And then that gives us the position of that new line. If it doesn't exist, we'll just print off that it's a syntax error, because clearly what we've basically done is, I don't know, we've probably got something like this, or we've got no like lines after it, which is a little bit weird. So we'll definitely assert there. And then basically begin. Begin is interesting. It's going to be the position, right, of this. So in other words, this will literally be 0, because the first time that we look through this, you'll see that in this case, it doesn't necessarily have to be 0. In this case, it's literally the first thing that we see in our file is that. But you can put other stuff here. You might have a comment here that says, you know, in fact, let's do this. We'll have a comment here that says basic texture shader, right? Just so that it kind of explains to us what this shader actually is. In this case, obviously, we have this stuff first, and then eventually we have type. So once we do run into type, that's going to be the position. From there, we take the length of the token, which is, and I should really probably just move this over here, because I keep referencing it so many times. So I'll keep this here. Hopefully you guys can see everything. So we're basically looking for the type token. So this type token length is going to be literally 5, right? Because it's 5 characters. So we advance past the beginning position, we advance 5 characters, so we're now here, and then +1. So that brings us, obviously because there's a space between the two, that brings us to type at vertex. Now, yes, I mean, look, if you really wanted to be pedantic, that's not going to work, right? Unless you trim the white space later, which you also could do. So in this case, we're just basically making sure that you have to have one space, otherwise you'll get like some assert and it won't work. Or it'll crash, in fact, because I haven't tested that, but whatever. So string type. So what we'll do here is we'll basically extract that type. So we basically take a substring from beginning to end of line minus beginning, right? So begin, of course, being the beginning of your token. So from here to the end of line, right? Which is going to be right here. And then if it isn't exactly vertex or fragment or pixel, right? We're going to say invalid shader type specified. Now, of course, that's just an assert, and I could easily just come up here and try and get the shader type from string, and if it returns 0, we assert. So we could do that. Could be a way to optimize this. In fact, I think I will do that. So we'll basically say shader type from string, and then type, because we know that if it returns 0, that in itself will check, right? It'll do this core assert here, but also it will catch another assert because this will return 0, and by asserting it, we're saying it has to not be 0. So invalid shader type specified. So yes, if you leave a space like this, right, it will in fact return an assert for you instead of crashing, which is good. All right, next line position, we find the next, find first not of, right? So we find the next line, and then from there we try and find the next type token, right? Which is going to be type fragment in this case. And then if we find it, all right, we do a bunch of stuff here. So let me just maybe tab this down and then try and split this up by parameter so you guys can see better. Basically what we're doing here is taking a substring from the next line position, which is basically the beginning of line 4 for the first time that we run this, right? We're taking a substring from that to hopefully what is the end, either the end of the file or the end of, like, until we find the next shader type, which is what this code is doing. And then after that, we'll of course go back up here and see if position is still not npos, which means that it found another token, and we'll rinse and repeat the process again. So that's kind of how we end up splitting this into several types. Now, of course, look, I mean, this code is not bulletproof. I'm not claiming that it is. You probably want to maybe clean this up, but for my purposes, of course, all I'm doing is splitting this up as quickly as possible, and this code is pretty simple and it works for most cases. But of course, if you do something stupid and you have like too many spaces, or you just do the wrong thing, it will most likely assert and let you know. Okay, cool. I'll just clean this up because I don't like the way that looks. And we can finally start feeding this stuff into our compiler. So preprocessor returns our unordered map. So now that we've got that, so we'll come over here. So we've got the shader source, right? Then we're going to get the shader sources, I'll call it, right? So maybe I'll just call this source just to make it a little bit easier to read. So we'll do our preprocess, which by the way could do other things. That's why I've called it preprocess. Could do other things as well. If we have other, like, maybe we have more than just type that we want to split on. Maybe we have other kind of metadata that we want to read out. So you can definitely do that as well. We'll give it the source, and now what we want to do is into compile, we want to pass our shader sources, okay? And so compile is going to take this entire code that we had in the constructor. We're going to get rid of it, and then we're going to go down into compile, which I don't think we created that, did we? So void Opengl Shader compile, and then here it is, our shader sources. We'll paste this in, and basically what we want to do is convert this into some kind of loop that will iterate over our shader sources map, right? So we'll say for auto key value kv shader sources. So just to make this super obvious, we'll have our glenum shader type, right? Which is going to be kv.first. And then we'll have our std string shader source. So we can just, I mean, we're obviously talking about shaders, so we'll just say type and source. And then that will be key value second. I'm taking that by reference, of course, because we don't want to copy a string. Now, since we are taking this in as a const, right, which is fine because we don't want to modify it, we'll just have to label this as a const string source. Okay, cool. So now that's done, what we want to do is, instead of creating this vertex shader, right, if I just copy this, and I'll probably get rid of the comments now, it's pretty clear what's happening anyway. GLUint will say shader type, right, or rather we'll just say shader. So this is going to be our GL create shader, and then instead of our vertex shader, of course, we're now taking in the type. So we're creating a shader of that type, right? Next line of code, actually, we'll just grab this whole section here and we'll kind of work through it. So next line, of course, we're taking in the source as a C string. So this will just be source.cstring. Instead of shader source, we now have, instead of vertex shader, we now have shader, right? And then this, which, what did that used to be? So we had source. All right, this used to be called source. I see. So we took that as a, we'll just say source C string to make that a bit more obvious. Okay, and then compile shader, which is going to be our shader. And this is obviously going to be shader again for the compile status. We'll get the log length, we'll do all of that stuff, shader. Now, in this case, it says vertex shader. Compilation failed, so we definitely need to have a way to convert that to a string. If we had the opposite of this function, we could probably use it. I'm probably not too fussed about this. We could just say like shader compilation failure, right? This is just directly from that OpenGL wiki. And then obviously we have an assert here, so it will kind of put a breakpoint here. And when we break here, we can easily take a look at what the type is and then see what it was. So it would be nice in the future to know what failed exactly, but I'm not going to bother with that now. Okay, so we'll kind of get rid of these comments, and I think that's it. So if you look at this, and we have a return here, I don't know if you necessarily want that. Maybe we'll just make it a break so that we don't keep compiling the rest of the shaders. But anyway, so that should be it. There's nothing here specific to vertex shaders. As you can see, we're basically compiling whatever the type is, right? And then we just create our shader, and then we use that everywhere. And that is pretty much it, right? So this kind of for loop now should compile both our vertex and fragment shaders, which is pretty cool. So we'll get rid of everything else. You can see how long this is. We don't need any of that anymore. If we come back over here, there's actually other stuff that we need, right? So now we have that GL create program, and then we need to attach all of our shaders, and then we need to link them, and then we need to do all of that, and then check the link status, of course. So this stuff can be fixed by simply reordering this stuff, right? So GL attach shader, for example, if the compilation actually succeeded, we can just attach it to our program by just attaching shader to program, calling attach here, after we've checked whether or not it's successfully compiled. Now, for that to happen, the program has to be up here. So what we'll do is we'll just take this and move it up here. Totally fine, so we create a program. Now the thing is, if it failed, maybe we want to set the render ID to something else and not program. Because of that, I think what I'll do is I will keep that GLUint program up here, and then we'll only assign the renderer ID to the program at the end. So that way we'll never end up with a valid shader program. It'll just be like 0 or whatever, even though I think 0 is valid. It will just be kind of not set until we know that everything worked out. So that way we can easily check whether or not a shader is in a successful state or not. So this disappears now. Everything else I think should work. The only thing that doesn't is this whole detach shader and delete shader business. So we need to basically keep track of the OpenGL shader IDs. Super easy to do, right? We know how many there are here. So what we should be able to do is easily just create a vector or something like this. You could create the thing is it's dynamic, so we can't really create it on the stack unless we use like allocate or something like that. So we'll just have a vector of GL enums, right? And this will be called our, we'll say GL shader IDs, right? And then into here we'll make it so that it's the right size. So shader sources dot size will be the size of this, right? So now that we've done that, all we need to do is come down over here, and then once we've actually created this, we basically just need to push this back into our shader IDs. Shader. Okay, so that's the enum being pushed back. So now we have a list of these. Now I can't remember if this actually creates that many elements or if it resizes it to that capacity, because we want the one that resizes it. So we'll see if this works. If it doesn't, we'll change it to be .resize, because I don't know, the API, I don't remember it that well. Okay, so that's pretty much it. Now if we want to like delete shaders or whatever, we just need to have a for loop that goes through all of that. So for order, in fact we can just, for order, we'll say ID in GL shader IDs, right? GL shader IDs. We'll go through and just delete that, and basically we'll do the same thing for this section here with detached shaders. So we basically just do that. Okay, so now we're successfully keeping track of all of that stuff so that we can later detach it, and everything is pretty much done. So if that is successful, we of course set our render ID to our program. We'll do that as the last thing that we actually do, so that in case we run into this, for example, it doesn't happen. And that looks pretty good to me. So now we need to fix it up for this, and that's pretty simple as well. Basically, all we need to do is create that shader sources thing. So std unordered, I'll just copy it. I was going to type it out and then I realized, why on earth would I do that? So we'll create this sources thing, right? And then into sources, we will add GL vertex shader to be our vertex source, and then GL fragment shader, of course, to be our fragment source. So fragment source. All right, and then now we can pass this into compile. We'll call this sources, and that's pretty much it, right? So we now support reading in from a file and splitting it up and doing all that stuff, but also you can just apply it manually. So we've got both of these, now we can test out both of these, right? So back in Sandbox app, texture shader dot reset, so Hazel shader create, this now becomes basically what we tested out before, which I think is, oh, it's here. So this is our texture shader, right? So we'll take this shader create that we wrote before, and we'll just pop it into here, Hazel shader create. And I think that should be pretty good. This is our flat color shader, which I think, are we still using? We're not using just the texture shader, are we? Okay, well, we had a triangle here. Let's maybe, I don't know if I want to bring back the triangle. So we've got this, oh no, we should still have our grid, right? That's our flat color shader. So that way we'll test if both the texture shader, which is loaded from a file, and then also the flat color shader, which isn't, make sure both of those work like they're supposed to. And of course we get some compilation issues. So let's take a look. Right, so GL-enum undeclared identifier, that's because we're not including OpenGL in the header file, so we can just do that. Of course, it's totally fine because the only place that we include that header file is going to be inside our shader.cbp, which means that we never actually see that GL header file inside the Sandbox app. Because if we did, it wouldn't work actually, so that's a good way to validate that. Okay, another build error, it's, oh, okay, so it looks like we are including it in a place that we shouldn't be because it's saying it can't open it. So that is interesting. I didn't think, oh, right, we are. The reason we are is because we're being super bad. We're including it here because we're actually dynamic casting it when we need to actually upload uniforms because we don't have a proper API for that. So that's terrible. We definitely shouldn't be doing that. Now you can see why that's a bad idea. So to kind of fix this up, really all I'm going to do is I'll get rid of the include here. I'll look at what GL-enum is, right? It's an unsigned int. So what I can do is just move this type def over here into our OpenGL shader. So this is of course to do remove because it's not what we should be doing, but it will make our code work for now. And the last thing we need to do is of course return that header file, otherwise none of our OpenGL definitions are going to exist at all. Okay, and as you can see, we now have this here. So we're taking in shaders both from files for this and then also the texture shader. Let me rephrase that. We're taking in shaders from just strings, which is this grid, and then these two textures are being taken in from a shader that is a file. Okay, so pretty cool stuff. We support both files and normal shader strings. I hope you guys enjoyed this video. If you did, you can hit the like button. You can also help support the series by going to patreon.com/the Cherno. As I did mention earlier, huge thank you to all of those supporters that make this series possible. Now we could go a lot further with this. In fact, I think next episode we might create something called a shader library. So at the moment, what we're doing is every time we need our shader, we have to kind of like load it, right? So what we do is we load our shader and then that's it. It's kind of maintained by ourselves. It's maintained by the client. That shader object is stored in kind of a variable that is inside our actual sandbox layer. Now, that's not great because if we suddenly want to use our shader all across our engine, right, we have no way of retrieving it. So we need something called a shader library, which is basically a kind of system that lets us just ask it for a certain shader by a certain name. So for example, hey, give me the texture shader, I want it. And then now we have the texture object, we can bind it, we can do whatever we want with it. So that's definitely something that we will explore probably next episode, but we'll see how we go because there's so much stuff to cover. I'll see you guys next time. Goodbye.